Fine. Okay, so record started. So welcome everyone. Today we have Yuanzhao Zhang from Santa Fe Institute, and we will have a nice talk. Let me check my notebook. A nice talk on twist landscape. High order interactions make basins deeper but smaller. And we will also have discussion on interdisciplinarity research. What does it mean to have an interdisciplinary job, and how to construct, how to deal with an interdisciplinary community of researchers, of scientists. So very nice topics. And so if you want to start, please, the room is yours.
Thanks. Is it Sylvia?
Yes, it's Sylvia. Sorry,
yeah,
I haven't introduced myself, but
no. I'm surprised that when you pronounce my last name correctly, everyone in the US pronounce it in a funny way, but okay. That's nice.
Hanlin give me his
Oh,
lesson before
okay. Great. Okay. Thanks for coming, everyone. Yeah, so today I'll just talk a little bit about our recent fun project, which we were trying to understand how high-order interactions change the not just the linear stability of different states, but also how those different states are organized globally. So I think most of people here probably wouldn't need me to go over those boring stuff, but yeah, so we have been studying network for over 30 years, and there are lots of fun and interesting results. But of course, now I think some of us are getting a little bit bored about networks, so we want to study something a little bit more complex. So people study hypergraphs and partial complexes, in which not just two nodes can interact with each other, but three or more nodes can interact as a group. So why do we want to study higher order interactions? Well, I think one appeal of the field is that it means different things to different people. For neuroscientists, they will say that it's because co-activation in the brain is important. And for people who study ecology, they will say that, well, it's because the existence of a third species can modify the interaction between two other species. And that cannot be modeled as a network or as a bunch of pairwise interactions. So you need high order interactions there. Or, in the more social context, whether it's diffusion or the spread of information or contagion, obviously everyone in the same room is different from everyone interacting in pairs. So high order interactions are helpful there. And for people who study nonlinear dynamics, which is where my background comes from, people would argue that it's because high order interactions, they emerge naturally when you do phase reduction. So, for example, when you have, say, a bunch of oscillators, and I think here they are phase amplitude of oscillators. So each of them has an amplitude, and also they also have a phase. So if you couple them physically to their nearest neighbors, and you want to simplify the description, so you want to only describe the system in terms of its phase. So you do phase reduction to get a different set of equations in which every node only has a phase, but hopefully still captures the essence of the dynamics. And when you do that, what happens is that all those dashed lines are those emergent interactions that didn't exist in the physical world, but when you do phase reduction, they kind of pop up naturally, and those are usually high order interactions that involve more than two nodes. So so that's why we think high order interactions are natural and worth studying. So today I think I just look at probably one of the simplest systems that we can look at that include a triadic interaction. Also, I think this particular form of interaction, it's one of the terms that emerge naturally when you do phase reduction. So the model is natural in this sense. So here we basically have a traditional Kuramoto oscillator model, where omega is the natural frequency of each oscillator. And today I will just keep it simple and assuming all the oscillators are identical. And sigma is the pairwise coupling strength, and we are normalizing it by the degree of each node. And Aij is the adjacency matrix. You have the normal sign coupling here. And then we add a new triadic coupling term in which you have the coupling strength, sigma delta, or rather, sigma triangle. And we also normalize by the number of triangles in our system. Bij is the adjacency tensor that tells you, which three nodes are connected. And we have this high order coupling term. So what we know about this system when we only have pairwise coupling? Well, lots of interesting things can happen, actually. First is that when the network described by Aij is large and sparse, then we can have extensive multi-stability in the system, meaning there are lots of coexisting attractors competing for the available phase space. And the more sparse the network, or the larger the network, usually you would have more attractors. So one particularly interesting case are the ring networks. In this case, we know that all attractors in the system are what people call the twisted states, which is shown on the left. So for each twisted state, basically, as you go around the ring, you would gradually increase your phase. And of course, as you go around the ring once, your phase could go from 0 to 2 pi for 1 time, for 2 times, for 3 times. That's what we call Q here, which is the winding number. So for Q equals 0, it's just the fully synchronized state. No phase is changing as we go around the ring. For Q equal to 1, as we go around the ring, the phase would go from 0 to 2 pi. And then for Q equal to 2, we will go from 0 to 2 pi here, and then we would do another full period. So so for the ring network, what happens is that if the network density is above around 68%, then the only stable state is the fully synchronized state, meaning Q equals 0. But as we decrease the network density below 68%, then when those twisted states with higher winding number would pop up one by one. So first the Q equal to 1 state would become stable, and as you further decrease the network density, Q equal to 2 state would be stable, so on and so forth. And I think in the extreme case, when you only have nearest neighbor coupling, then I think you can have n divided by 4 number of twisted states that are stable. So, a natural question about the system is then, how are those different attractors dividing the phase space? So for example, what are the size of the basins for those different states, and how do they look like? So there's been lots of studying looking into, for example, the scaling relation between the size of the basin and the winding number. So it turns out, so here P just means the basin size. So the basin size of the twisted states with winding number Q actually scales as e to the minus k to the q squared. So it decays very rapidly. And on the other hand, those basins, they actually looks very complicated. So in particular, you cannot approximate them with some simple geometries we are familiar with, for example, like hypersphere or hypercubes. Instead, they have those tentacle-like structures that kind of sprouting out of the the vicinity of the twisted state. And because of the high-dimensional nature of the phase space, most of the basin volume would be concentrated in those tentacles instead of the core region of the basin. Okay, so enough about the pairwise case. So what happens when we add triadic coupling? And in particular, today, let's consider just a simple ring structure. So for the pairwise case, we have pairwise, we have R coupling on both sides. And we do something similar for the triadic coupling. So basically, if we use the AIJ and BIJK language, we set BIJK equal to 1 if and only if I is different from J and J is different from K. And we also require that J is within distance R from node I, and node K is also within distance R from node I. Equivalently, maybe more concisely, you can also say it's like Bij equal to Aij times Aik. Okay, so that's our system. What can we do about it? Well, first we can do linear stability analysis and see how does the linear stability of those twisted states change as we say change the triadic coupling strength sigma triangle, right? So how do we do that? Well, it's not that difficult because every twisted state is a fixed point, and to analyze the linear stability of a fixed point, well, you just write down their Jacobian and calculate their eigenvalues. So here, for an arbitrary fixed point sigma star, you can, well, of course, we can write the Jacobian as the sum of the contribution from the pairwise term and the triadic term. And if you just do the calculation, you will see that the for off-diagonal terms, the Jacobian is given by those formula. For example, this is basically just taking the derivative of the sine function there, and you do something similar for the higher order term. And for the diagonal term, it turns out that the Jacobian is kind of a Laplacian matrix. So each diagonal entry, it's basically the row sum, the sum of all the off-diagonal entries from that row. and you add a minus sign in front. So the row sum of the Jacobian is 0. And one nice thing about the ring structure we're considering is that the Jacobian matrix is what people call the circulant matrix. So you can see here, in the first row we have J0, J1, J2. It's also a symmetric matrix. That's why we end up with J2 and J1 in the end. Then for the second row, you're just shifting everything to the right by one slot. So J1 goes from here to here, J0 goes from here to here, J1 goes from here to here, and you do this shift for every row. And the nice thing about this circulant matrix is that we can write down the eigenvalues and eigenvectors analytically. So here, lambda p is basically the eigenvalues of this circulant matrix J. P is indexing the eigenvalue, and JS is basically all the different entries in a row. And N is basically the size of the matrix or the size of the network. I think I have explained everything. Okay. So then with this formula, then we can try to see what's the linear stability of all those different twisted states when we have both pairwise and triadic coupling. Basically, you take the previous formula, and you would get and you can get the JS for the twisted for the ring structure and twisted states. So one nice thing about the system is that when S is larger than the coupling range R, then all the JS is equal to 0. So in this sense, it's much easier to write down the formula for the Jacobian is simpler when you have a more sparsely connected structure. So for example, for R equal to 2, then we only the only non-zero off-diagonal term in the Jacobian is J1 and J2, and we can write them down very simply as just kind of sums of different harmonics. So okay, so enough about mathematics. Let's plot. Well, let's plot the largest eigenvalue that's not 0 in our system, and see how does that change with the triadic coupling strength. So here I'm plotting lambda max, which determines whether the twisted states is stable or not, as a function of Q, which is the winding number, for a system with 83 oscillators. So for example, this point would represent sigma triangle equal to 0, so only pairwise coupling, and Q equal to 0, which means full synchronous state. And you can see because lambda max is below 0, it means the system is that particular state is stable. So okay, so let's look at the plot for sigma triangle equal to 0. Well, you can see it has kind of 3 prominent peaks, and it starts negative, but I think after around Q equal to 11, it goes above 0 and goes into this part, means, well, the twisted states becomes unstable for Q larger than 11. By the way, I think there's a symmetry between left and right. So actually, Q and the Winding number Q and Winding number N minus Q actually represent the same state. So we can just look at the left half of the plot. So as we increase the triadic coupling strength, you will see that the two side peaks gets flattened very, very quickly, whereas the central peak gets more and more prominent. So as a result, if we zoom in around the lambda max equal to 0 part, you will see that as we increase the sigma triangle, more and more Q twisted states would become stable. For example, for pairwise coupling, it's only stable for up to Q equal to 11, whereas for sigma triangle equal to 4, it can be stable for up to Q equal to 33 or something. So it's a very significant improvement in terms of linear stability. And another interesting thing I want to mention is that because the function of lambda max versus Q is non-monotonic, so it's kind of increases but then decreases for certain Q. What can happen is that you can have Q on disjoint interval that get stabilized. For example, for sigma delta equal to 1, which is this curve, you will see that it's stable for, until Q around 15, then it becomes unstable for Q equal to, from Q equal to 15 to Q equal to, say, 23. Yeah, but then it becomes stable again from Q to 23 to say around Q to 30.
Sorry.
I think you can working.
What's up, guys? It's Quandale Dingle here.
Okay.
Rhymes, including battery on.
Okay. I don't know who he or she was, but I removed that so we can continue.
Okay, yeah. Well, that's.
I tried
fun.
to mute them,
Mhm.
but they still, I don't know,
Yeah.
to unmute, and so yeah, I kicked them off. I don't know. Okay, sorry about that.
No worries. It's fun intermission.
Yeah.
So yeah, so like just maybe to make it more intuitive, we can plot the percentage of stable twisted states as a function of the triadic coupling strength, and you can see that it's monotonically increasing, and it goes from say around 30% stable twisted states all the way to more than 80% of the twisted states becoming stable as we introduce triadic coupling. So the blue curve was for n equal to 83, and if we make n larger, it basically just makes the curve smoother because now we have more twisted states to look at. But the curve basically look very similar. Okay, so that's linear stability. So high order inductions significantly improves linear stability in this case. So what about basin stability, which is basically just means how do the size of the basins of those twisted states change? So here what we did is basically, we basically just started from a large number of random initial conditions sampled uniformly in the phase space, and then we count how many initial conditions goes to each twisted states. So as you can see, when we increase sigma triangle from 0 to 1, well, nothing much happens. The Q to 0 basin becomes a bit smaller, the Q to 4 basin becomes a bit larger. But as we increase sigma triangle from 1 to say 3, then something dramatic happens. So the basins for all those twisted states, they start to shrink very rapidly. Whereas the basin for all those other states that are not twisted states, which we mark as non-twist here, it rises rapidly and approaches 1. So here is a more maybe visual representation of what's going on. So what I'm doing here is I'm taking a 2-dimensional slice of the phase space, and I'm coloring, this 2D plane according to which basin would each point converge to. So, for example, if it's red, then it means we start from that point, the system would evolve towards Q the twisted state with Q equals 0. Another thing I want to mention is that the origin of the plane, I set the origin of the plane to be to correspond to the twisted state with Q equal to 12, which we know from linear stability analysis is unstable when we only have pairwise coupling. So that's why you will see that even around the origin, we don't get any basins that correspond to Q to 12. Instead, we have it, goes to like Q to 6 or something. So next we increase sigma delta to sigma triangle to 1. And in this case, from the linear stability analysis, we know the Q equal to 12 state now becomes linearly stable. So that's why you will see this blue basin emerging around the origin. Then when we change sigma triangle to 2, well, the Q equal to 12 basin expands a little bit, but the most striking feature is that you have all those black regions emerging, which represents the phase space being taken over by the non-twisted states. And at Q to at sigma triangle equal to 3, the black is basically overwhelming the basins for twisted states. So one thing that might be counterintuitive is that although the blue basin, the Q equal to 12 basin, looks kind of significant in this last plot, if you start from random initial conditions, actually you would never find it, because the phase space is so high dimensional. For example, if we assume that we have this blue basin, let's say, that's for alpha 1 equal from minus pi over 2 to pi over 2, and the same here, then it's like, okay, for each dimension, you want to flip a coin, and if the coin is facing upward, then it's check. Okay, then for 83-dimensional system, in order to get to this basin, you need to flip your coin, say 83 times, and every time it should face upward. If that happens, then yeah, you can get to that, but usually you cannot. So finally, I'll just, I think maybe one question we all have would be, so what are those non-twisted states? How do they look like? So here the three insets are basically the typical states you would get if you run simulation from a random initial condition. So for small sigma triangle, of course, you would reach one of the twisted states. For intermediate sigma triangle, you would actually reach those interesting chimera states that for part of the ring, the oscillators behave very much like a twisted state, whereas for the rest of the ring, the oscillators are disordered. And of course, eventually, when sigma triangle is large, then the typical state is fully disordered. And maybe, okay, one thing I want to remind everyone is that although this is fully disordered state, those twisted states, they still exist and are more stable in this large sigma triangle regime. It's just you will never see them from random initial conditions. The rest of the plot is basically just the percentage of oscillators that are ordered. So for twisted states, every oscillator is ordered, whereas for disordered state, every oscillator is disordered, kind of. Okay, so one last thing I want to say is that the coupling structure I've been talking about, it's not the only interesting coupling structure. So you can, there are also natural ways to add triadic couplings that respect the rotational symmetry. For example, imagine you begin with a ring network. What you can do is that you can turn that ring network into a simplicial complex. So that's another way to introduce triadic coupling. And more mathematically speaking, what happens when we make this simplicial complex is that we make Bij equal to 1 if, again, I not equal to j, not equal to k. And again, j is within distance from I, k is within distance from I, but also we also require that j and k also within distance r from each other. And that basically means Bijk equal to Aij times Aik times Ajk. And we also studied this system, and the same thing happens. So when we introduce triadic coupling, the linear stability of the twisted states becomes better, whereas their basin shrinks dramatically. And yeah, so this is a fun project we did recently with Max, Fede, Seb, and Jill. So there's an archive if you're interested. Yeah, and that's it. So, and assume I don't know what happens next, like whether people want to ask questions or we can have some tea time, whatever.
I mean, if there is someone that want to ask something about the research part, we can talk about it, or we can leave all the questions and comments at the end. I mean, after the time or during the tea time.
Well, I actually didn't have any slides for the tea time. I just want to maybe have any like conversation, like whatever we are frustrated with. Yeah,
it's totally fine. If you have any question, you can either unmute yourself or raise your hand, or you can post it in the chat so we can read that. I mean, I have a curiosity. One is more about the interdisciplinarity discussion that we can have later, so I'll leave it to later. The other one is I'm kind of curious about the winding numbers.
Right.
I mean, I'm not very into Kuramoto oscillators, so maybe it's a silly question, but I'm curious on why for example, Q11, and
Mhm.
after you have instability, if there is some like pattern there with these integer numbers. And
Mhm.
the second question is more like on practical, if you want to, it's more like on a measure that I was thinking on. Do
Mhm.
you have a measure of how hard is to find this basin? Because you mentioned that if you have you made that example of the coin. If you have a
Mhm.
coin and if you want
Mhm.
to get in the blue
Mhm.
basin by chance, it's
Mhm.
very hard. So I was wondering if in the archive or maybe in the literature is kind which measure of this randomness or of this deeper, so the
Mhm.
difficulty of getting to the blue basin, and
Mhm.
which
Mhm.
measure
Mhm.
you use to quantify, if you
Right.
want, this
Mhm.
this thing.
Right. So for the first question, maybe you can clarify a little bit. What do you mean by pattern? Are you asking, is there any sudden shift in terms of pattern when we go from Q to 11 to Q to
Yeah,
12?
that one exactly, because we have the stability and instability, right?
Mm-hmm.
Yeah, that's my question. Why at that Q is there?
Oh, yeah. So no, like in terms of the twisted states themselves, the pattern doesn't change very much, right? So basically, Q to 11, the oscillator phase just rotate, just
Yeah.
twist around the ring for 11 turns. For Q to 12, it just twist for 12 turns. But of course, you will see from here that there's a huge jump in terms of
Yes.
stability, right? So what happens here is that because here we are plotting the maximum eigenvalue, so what happens here is that there is some crossover. So this branch used to be the largest eigenvalue, and what is not shown is that for say for the second largest number, it used to be somewhere here. And at this point, they kind of cross each other. So that branch becomes the largest one.
Oh, I see.
And then there's and the slope is much steeper for that branch. So you have a huge jump
I see.
there.
I see.
Yeah. So the patterns themselves are very similar.
Okay. Thank you very much.
For the second question, yeah, like I think there's a 2013 Nature Physics paper where people talk about basin stability, and yeah, basically how they define it is just like basically the relative size of that basin compared to the entire phase space.
Yeah.
So the probability of finding that basin starting from random initial condition. Then they calculate that by doing a bunch of Monte Carlo simulation, stuff like that.
That's cool because it's a multidimensional space, right? So you only show size. It seems large, but it's not if you think multidimensional.
Right. And yeah, so for example, for that blue basin, it'd be very, very hard to estimate its size just by doing simulations from random initial conditions because its relative size is so small.
That's pretty interesting. Thank you for the answers. Is there any other curiosity or question about this work?
I might have a question regarding the high point at around, I don't know, 40, 42, 44, something around this. What is the significance of the winding number where this like what is the symmetry point? What is it? I have not seen it, but it looks very nice.
What do you mean significance?
Yeah, what does it mean? The exact value of the symmetry point where you have these growing instability. You know what I mean? At Q, at the winding number equals,
Yeah,
what is
here?
it?
Mm-hmm.
Yes.
So I mean, this is basically the symmetry point, right? So you know, like so basically, I think you have a peak here exactly because of the symmetry. So basically, here we have 83 oscillators, and for a system with n oscillators, twisting the oscillators one time is kind of exactly the same thing as twisting the oscillators n minus 1 times. So if you write down their respective phase, they would actually be the same. So that's why here and here you have exact symmetry here, and Q for the 142 or something is basically the the symmetry point. Yeah, I don't know whether that answers your question, but
Yeah, thank you very much. That answers my question.
okay.
Is there any other question? Thanks, by the way, because I missed too the number of oscillators. So I was also wondering what why the
I see. Yeah. I mean, we have to simulation for a particular n, but as you can see, it doesn't change
yeah
as we make n larger.
it's cool. If we don't have any more questions on this part, but we can go back on these also later if any ideas pops in your mind. Maybe we can go on the discussion part. So I don't know if you want to like introduce the topic about the interdisciplinarity community and all the stuff. Maybe we can then discuss.
Right. Yeah. So I think I just maybe like, I don't know, we can just complain or whatever. Yeah. So I'm happy to discuss anything, but one thing that came to my mind would be maybe many of us are facing will be finding a community as an interdisciplinary scientist. Oh, what is this?
I tried that thing, but I don't know. Maybe it was better.
Now we are all in a black hole.
Okay. Well,
Okay. Yeah, like how do we find our community? Or like more practically, how do we find a job eventually? So well, both parts I'm still struggling with. So don't look for me for advice. I don't have any. Yeah, it's just like, so if I imagine some of us are in a traditional department, and maybe sometimes we feel we don't fit in very well. So for myself, I did my bachelor's in mathematics and I did my PhD in physics. And I mean, I always consider myself kind of a fake physicist because I'm really bad at physics. Yeah, and like, there just wasn't too many people, say, in the physics department that share my interest, or have similar background. So sometimes it's frustrating. But yeah, so yeah, I'll be curious to hear how you guys, whether you guys have the same problem or how you guys deal with it.
I kind of the same problem, if you want to call it problem, because I mean, in a school of mathematical sciences, but I'm more like a physicist, and also I'm more like very applied, while I'm surrounded by pure mathematicians or statistical scientists. So sometimes it's kind of, yeah, isolating if you want. But I was lucky because I also had like a small group of complex systems researchers. So, I mean, that wasn't so hard at the beginning, but I mean, sometimes it is because the largest, if you want, the largest part of the school is made up by mathematicians, and sometimes if you don't have a very like theoretical direction in your research, can be hard. Like try to find someone to ask for like help if you have a problem. But when you have a theoretical problem, it's wonderful because you have many people working on like I don't know, everything in like sequences and series and functions, and you have kind of everything. So I mean, it has its pros and cons if you want. And I wanted to ask you, or I mean, if anyone want to share anything, because I know that Violeta, for example, is in a kind of interdisciplinary environment, right?
Yes. Hi. Well, actually, I have just started my new postdoc.
Oh,
so
sorry.
no anymore. But I mean, even if I was in a very interdisciplinary atmosphere, maybe sometimes I felt that some of my topic of interest were not truly represented there in that cohort of interdisciplinary people. So the thing that I did was to go online and to try to find on especially in Twitter, those communities of other people that were also from my age, more or less, and that were studying cool things. And I mean, it was quite difficult to just go to academic Twitter and find someone. And one thing that helped me was to look for schools. So especially now during COVID and post-pandemic times, that they have a lot of schools online. Those schools for me were a wonderful opportunity to get to know people with more interest in common for me. Yeah, that's what I can say, I think.
Yeah,
I don't
no,
know if you have similar experience.
I strongly agree. Online collaboration is so much easier nowadays. For example, like four of those guys, three of them I haven't met in person. So, I think it's very easy for us to find our community or likely-minded people online. You know, just reach out on
or going
X
to conferences
or whatever.
Yeah, whatever is called now. I had another question regarding the job, because you mentioned also interdisciplinary jobs, like how hard is to find interdisciplinary jobs. But what do you mean? Do you mean inside academia? Try like how is it going from, I mean, from a department to another, from a school to another, or from like becoming like an interdisciplinary, I don't know, consultant out academia, or what?
Yeah, I think it really depends on what you want, right? I would say just like keep an open mind and see other options. For me personally, I've been like looking for faculty jobs recently, and it's kind of first, like, you need to monitor a bunch of different you need to monitor jobs from a bunch of different disciplines,
Yeah.
which is a lot of work. But also like, I guess the frustrating part is that, like very often it doesn't seem like a very good fit. So, if a mathematics department wants to do some general search, then I probably know that I'm not the one they're looking for, kind of thing. So yeah, but I don't know too much about industry, but maybe it's more receptive to someone with a interdisciplinary background than a traditional academic department. I'm not sure.
Yeah. I'm not sure.
Well. But I guess before the faculty stage, I think at the postdoc stage, there are actually lots of very nice interdisciplinary fellowships. That's kind of, I think, would be a nice fit for many of us. By the way, the SFI fellowship is due tomorrow. Is anyone? Is
Good.
Maybe next year, not today.
That's good. And yeah, I mean, I really agree with what you said about keeping an open mind, because I was actively looking for postdocs position as well, like last 2 months. And I mean, I talk with many people, and some of them were very like not positive about, not optimist about the fact that they will find a position, because they were like, oh no, but I'm doing research in this field. There are so few positions. It's very difficult to get there, and stuff like that. But in my specific case, that I'm very interdisciplinary. I mean, I based my PhD on 3 different projects on very different fields of applied mathematics and networks, if you want. So for me, it was like, I mean, I get like 3 interviews, 2 of them, I mean, in a month, only because I looked for some like applied projects, and wasn't so hard. I mean, if you have an open mind, and if you want to go outside your comfort zone, and if you want to like try to use your methods, your mathematics, your ideas into like some like interdisciplinary projects, or people that needs maybe a physicist, maybe a mathematician to kind of solve some problems. I mean, I don't think I was lucky. I mean, I think I believe in probabilities. So I think it's only like, it's only a matter of being open to this kind of jobs. And hopefully will be also fun to do. I mean, to change a bit, to go outside the comfort zone.
Right. And I think one thing I want to add is like, don't undersell yourself. Like, it's tough, but I think we will all find a good job we like eventually. So like, if there's a job that you're not so sure about, either because the location is not very ideal, or the pay is very low, or you just don't like the person you're working with, don't feel like you have to take that offer, or you have to stay, because it might be difficult to find a job elsewhere. Like, yeah, just don't undersell yourself.
Yeah,
Go on, Violeta.
Okay, that related to that, I have an idea. I don't know what will you think about it, and it's like, for some people, being an interdisciplinary scientist is like a robot. It's like something bad because you are not, you do not completely fit in his or her job position. So, but what I want to do is that to turn that around 180 degrees. And when I present myself as a physicist on complex systems or as an interdisciplinary scientist, I try to emphasize that actually this is a positive thing, because I've been able to dive in literature of very different fields, and now I know how to read papers of social stuff and ecological conservation and phenology and very different things, and also that I have a robust toolbox that I'm able to apply to very different problems. So actually, if you are hesitating about how you should sell yourself for a postdoc position or something, just try to emphasize that this is a very positive thing, because that means that you are a very hard work person that is able to adapt very well to the environment. What do you think? Do you also do that? Or
no, I definitely agree. It's a wonderful thing. It's our strength. But I don't think we need, or well, I don't think we need to sell it. Like if someone thinks like your interdisciplinary background is bad, don't work for that person. Don't.
True. True. That's true.
Red flag.
Yeah, like, yeah, I think like there are lots of people who would appreciate our diverse background, and they will see it as a strength, and more people are becoming like that. So I don't, yeah, if you see someone that's the opposite, I would say just run away. It's not worth wasting your time.
And also, if I can add a thing, is that we are also unbiased on the field, because I mean, we can look at it with the pure eyes of mathematics or physics, if you want. So I think it's totally a strength. I agree with Violeta, and I also agree that if someone seems to say that your background is bad, is like a red flag.
I maybe have a follow-up question, which is, let's say I have a job in interdisciplinary science. My guess is that Santa Fe is a great place to do interdisciplinary science. At least that's how they present themselves. So my question would be, what can an institution do to nurture and enable people to work interdisciplinary? Because just because they are close geographically or in the same building does not mean that they work together. They have to be like shaken a little bit to work together, right? Because they are a little bit different. So maybe can you tell what in your experience helped the interdisciplinary I don't know how to end the sentence.
Right. Yes, it's no, I don't have a clear answer. It's, of course, there are some things the institution can do, but it also depends a lot on, timing and like the chemistry between you and the other person, and it's just such a complex process. So I think there are a few things SFI is doing that I like. One is that they give you this every year they give you this what they call the collaborative fund. So you can use for any purpose related to collaboration. So you can invite someone to visit you at SFI and trap them for a week. So you can get some ideas going. Or you can visit someone else, or you can just find someone else also at SFI and do something fun together. So yeah, so I like that mechanism. It's not like, because different people want different things to facilitate their collaboration. So just give us the money and we will do the rest. But yeah, like there's also something called like 72 hours of science at SFI, which is basically a lot of postdocs get together, rent an Airbnb, and try to work on one project together for 3 days. And the goal is to write an archive paper at the end of the 72 hours, which was fun, but the paper part didn't happen for the last 2 years. And I kind of have mixed feelings about that thing, because it's kind of hard, like when you have 10 different people with such a different background in the same room and trying to find one thing to work together. Usually the group would gravitate towards not the most interesting or exciting project, but the project that everyone can do something on. So yeah, so it's complicated, and yeah, I'm still figuring it out. I'm sure everyone's still figuring it out.
Maybe create smaller groups. I don't know. Like 4 or 5 people, but stay all together. I don't know, something like that. Them presenting the works to the groups. I don't know, something like that.
Yeah.
It's difficult to find intersection between 10 fields.
Right. Yeah, exactly.
But it seems nice.
Are there maybe any more questions from the audience or from other people? You can also type it in chat if you want.
Otherwise, if there is no more comments, maybe we can end. What do you think, guys? All right. So yes, we stay 10 minutes longer, but oh, hi, Onkar. But was worth it. Okay, thank you again. Thank you very much for the talk and for the discussion. We can continue the discussion through the Twitter or the other platforms that we have. And thank you again, and see you next time at Netflix.
Yes, thanks for coming, guys. Have a nice evening.
Bye-bye.
Bye-bye.
Bye bye. Thank you.
Bye-bye.
Thank you. Bye.